Okay, let's dive into this. Have you ever really stopped to think about what exactly happens the split second you click sign up on a new website? I mean, you type in your email, you carefully craft a secure password, and then what? Well, today in this explainer, we're taking a structured, behind the scenes look at the actual life of a password. We're going completely under the hood to see exactly how developers take your most sensitive information and securely handle it on their backend servers.
Here is our roadmap for today. We are going to cover building the initial sign-up flow, the massive danger of plaintext passwords, hashing with Bcrypt, the login comparison process, and finally, what comes next with JWTs. Let's get to it. Starting with Section 1, building the sign-up flow, setting up the database.
So before we can secure a user, we have to actually create one, right? We use backend tools like Express and Mongoose to route data into a Mongo database. But to do that, the server needs a blueprint. In database terms, this is what we call a schema. Think of a schema as a really strict checklist of the exact fields we want to save. For our test user here, we're requiring 3 essential pieces of info from that initial HTML sign-up form: their name, their email, and their password. And right now, at this exact moment, everything here is coming in as raw, plain text.
Let's trace how this actually builds out our logical sign-up flow. Step 1 is just receiving that request body data, the name, email, and password the user just submitted. But step 2 is an absolutely crucial checkpoint. We have to check the database for an existing email. We use the database's find method to search for that specific address. Why? Because you can have a dozen users named John Smith, but every single email address must be unique. If we find a duplicate, we throw an error and stop the whole process dead in its tracks. If the email doesn't exist, we rapidly move to step 3, which is creating the new user, and finally, step 4, sending a success response back to the browser. Moving to Section 2, the plain text password danger, the critical security flaw. So the crucial point is, we've successfully created our user, but we've just made a massive, dangerous rookie mistake in our code. We literally took the exact password the user typed and saved it directly into the database as raw text. This quote from our source material really highlights the severity here. It notes that if any hacker hacked this database, he can directly see the passwords, or even if developers can directly see the information. And that's the kicker, right? This isn't just about outside hackers and hoodies. If you save a raw password, internal developers working at big organizations, think of a giant company like Facebook, could theoretically just open up the database and directly view your private data. That is an absolutely unacceptable security practice. And this brilliantly illustrates the stark contrast. On the left side, we have a raw, hard-coded password. Someone typed in 1234, and the database simply saved 1234. On the right side, we have a hashed password, a completely random-looking string of binary or hexadecimal characters. I mean, the difference is night and day. You can immediately see why saving the raw version is a terrible practice compared to an encrypted, unreadable string. We desperately need a way to turn the left side into the right side. Which brings us to Section 3, hashing passwords with Bcrypt, the cryptographic hero.
To fix our plain text nightmare, we're going to install an NPM package that basically acts as our ultimate defender. Bcrypt is a package used to change a raw password into unreadable binary or hexadecimal code to secure user data. Its entire job is to intercept our vulnerable password in the code, mutate it, and turn it into complete gibberish before it ever even has the chance to hit the database.
Now, what's really fascinating is how Bcrypt actually pulls this off. It uses something called a salt. A salt is a random 10-digit string generated by Bcrypt itself. Think of this like baking a cake, okay? If your password is the flour, the salt is, well, literal salt. Once you mix that random 10-digit string into the raw password, the ingredients are fundamentally transformed. You cannot unbake the cake. You can't separate the salt back out from the flour. The original password is gone forever, replaced entirely by the final hash. Here is that process step by step in the backend logic. Right before the database save actually happens, we intercept the flow. Step 1, we tell Bcrypt to generate that 10-digit salt. Step 2, Bcrypt takes the raw password, mixes it with the salt, and hashes them together. Step 3, we output the newly hashed password directly to the database. So now only the user actually knows their real password. The server is just holding on to the encrypted result. Section 4, the login comparison process, verifying the unreadable. So the user comes back to our website a few days later and wants to log in. We've successfully secured their data, but we've accidentally created a brand new challenge for ourselves. Think about this question for a second. How do you compare a password you literally can't read? The user is typing 1234 on their screen, but our database just has a giant random string of hexadecimal characters. We can't unhash the database entry to check if it's 1234, because remember, Bcrypt is a strict one-way street. So how on earth does the server know if the user is typing the correct password?
The answer is the Bcrypt compare method. Just like Bcrypt has a built-in tool for hashing, it actually has an incredibly elegant built-in method specifically designed to evaluate a fresh login attempt against that encrypted database entry.
Let's break down the exact logic of this login check. First, we take the input email to find our specific user in the database. Then, here's the magic trick. Instead of trying to unencrypt the database, which we can't do, we take the new login password attempt and we run it through the exact same encryption blender. We mix it with the same salt, and we hash it. Finally, the compare method looks at our newly generated encryption, looks at the database encryption, and checks if they match. All of this incredibly complex cryptography ultimately boils down to a beautifully simple Boolean value, true or false. If true, the passwords match, and the login is a total success. If false, the user is rejected.
And finally, Section 5, the next step, JWTs, the stateless problem.
We've built the schema, hashed the password, successfully compared the login, and the user is officially inside the app. Time to celebrate, right? Well, actually, scratch that. We have an immediate cliffhanger to deal with. Have you ever experienced this frustration? You log in successfully, you click a link to go to your profile page, and suddenly, bam, the screen asks you to log in all over again. Why did that happen? Because by default, web servers have complete amnesia. The internet operates statelessly. Every single time you move to a new page, the server forgets who you are. It basically looks at you and says, who are you?
The ultimate solution to this server amnesia is found in cookies and JWTs, which stands for JSON Web Tokens. This is data created by the server right after a successful login. The server creates this token based on your password and a random string and hands it back to your browser. Your browser then stores it. From that point on, every single time you click a new page, your browser silently hands this token back to the server, like an exclusive VIP pass. It proves your identity, so you don't have to enter your credentials over and over again.
And that perfectly encapsulates our journey today, the hidden complexity behind a deceptively simple login button. From database schemas to duplicate email checks to the cryptographic heroics of Bcrypt generating salts, comparing Boolean values, and finally issuing those JWT VIP passes. All of this intense back-end logic happens in the absolute blink of an eye when you interact with a web form. But you know, as computing power continues to grow, even robust tools like Bcrypt are going to face new threats. So the next time you click login, ask yourself, in a world of quantum computing and rapidly evolving hackers, exactly how long will our current cryptographic heroes keep our secrets safe? Thanks so much for joining me on this explainer. I really hope it brought some serious clarity to the invisible world of web authentication. Keep learning, and I'll catch you on the next one.